Greetings, everybody. Let's continue our discussion of trigonometric integrals. So we've kind of gone through the cases where we were dealing with products of powers of sines and powers of cosines. And so now we kind of move on to the case where we're dealing with powers of secants and powers of tangents. And so kind of also along those lines to kind of guide our thinking in what we were doing, kind of remembering some formulas that come into play. That if we talk about the derivative of tangent, remember that we get secant squared. And if we talk about the derivative of secant, there remember that we get secant of x, tangent of x. And then kind of the big trig identity that's also going to go along with this when we're doing any of these problems is our 1 plus tangent squared being secant squared. And so rearrangements of that trig identity along with our derivative formulas are really going to be the heart of our strategies in kind of dealing with these trigonometric integrals. So kind of what you've seen before in some of the prior videos, we know that we were doing kind of the strategy was really to take, if the powers were such that we could take out a du, take out a power and it becomes part of our du to then become a u substitution, that's the same kind of strategy that we're going to employ for some of these. And so kind of the first case that we were looking at is what we can do when the power on secant happens to be even. Okay, so that's kind of our first strategy. The power of secant is even. Okay, so what happens in that case? Well, the idea is we come back to our derivative formulas. And if the power of secant is going to be even, remember that if we do a u substitution with tangent, that the derivative of tangent is going to be secant squared. And so we kind of keep two powers of secant back for our du, and then we want to be able to convert the other power of secants, the other powers of the secants, into tangents. And so the idea is we convert the remaining powers of secant to tangents using our trig identity, secant squared is 1 plus tangent squared. And that's kind of going to be our strategy to deal with these particular cases. So let's actually work out this example and see how it goes. A couple of powers of... So what we've got is the integral of secant to the fourth times tangent of x dx. Okay, so if we've got a secant to the fourth, well, we take out a couple of powers of secant, and so that's going to leave us with a secant squared and then a tangent, and then we've got a secant squared of x dx. So this is kind of in reserve for what will become our du in just a little bit. And so we want to do a u substitution. So we want a u substitution with u equal to tangent of x, du becomes secant squared of x dx. And so we need to convert the last powers of secant into some expression involving tangent. And so we do that with our trig identity that secant squared just becomes 1 plus tangent squared. And then we've got our tangent on the outside and our secant squared of x dx. And so now, sure enough, we can go forward with the u substitution. So this thing is really going to look like 1 plus u squared times u times du with that substitution. So we end up with just this polynomial u plus u cubed du, which we can just integrate as 1/2 u squared plus 1/4 u to the 4th plus c. But then kind of coming back to our variable x, that really just gives us a 1/2 tangent squared plus 1/4 tangent to the 4th plus our arbitrary constant. And sure enough, that gets us exactly where we want to go. And so in this case, what made this particular strategy work was the fact that we had the power on secant being even. That was really what we needed to make any of this happen, because then we could take out our secant squared. We can remove, we still have an even power left over when we took that out to then convert all of the other powers of secant into expressions involving tangent, and so we could go forward from there. And so this is kind of one of our strategies to deal with. If the power on secant is even, then we know what we need to do, and we can go forward from that. So now let's pick up on another example. All right, so in this case, now let's see what happens when the power on tangent happens to be odd. And so what we can do in this case, now kind of the flip side, the first case we kind of did, we wanted to do a u substitution involving secant. So in this case, we want to go to get a u substitution with u being secant of x. And so what we need then is for du, derivative of secant becomes secant of x, tangent of x, dx. And so what we kind of need for our du, we need 1 power of tangent, and we need 1 power of secant for this thing to work. And so in the cases that we've got that, let's see what happens. Well, we take our integral of secant tangent cubed. We take out a secant and a tangent, so that we've got a tangent squared, and then we've got our secant of x, tangent of x, dx. So this part ends up becoming, so we know this part is going to end up becoming our du, and so what we need to do on this in order to do the u substitution, this one we need to convert to some expression involving secants. And so what do we do with that? Well, we quite simply use our trig identity. And so what happens in that case is our integral of tangent squared becomes secant squared minus 1. And then we've got our secant of x, tangent of x, dx. So that now with our u substitution, we get u squared minus 1 for our substitutions. We get our u squared minus 1, and then our du for our secant of x, tangent of x. And so in the case that our power on tangent happens to be odd, we can employ this strategy as long as we've got some secants around that we can borrow from as well. So what happens in the case where we don't necessarily have that? So let's take an example now where we just have let's just say it's the integral of tangent cubed. Okay, so now we've got an odd power of tangent, but we don't have any secants to borrow from. And so what happens in that case? Well, we can still take out, if our power on tangent is odd, we can take out one power, and so we've got an even power left. And so with that even power, we still go forward and do an integration, or we still go forward and we can make our substitution with our tangent so that our tangent squared then just becomes a secant squared minus 1, and then we've got a tangent of x dx. Well, if we go ahead and distribute from that, what happens now is we get our secant squared of x times tangent of x. Now we do have a power of tangent left over, but then we've also got this lone tangent that we have to deal with. And so we can break this up into two separate integrals. So secant squared of x, tangent of x dx, minus the integral of tangent of x dx. So this first one that we have, what we can do with this one is now we are kind of back in that case where we've got an odd power of tangent, but now we do have powers of secant that we can also borrow. So we can form, in this case, we can form our secant of x, tangent of x, dx to become our du in that case. And so we are kind of back into the situation where we can do exactly what we did in the previous problem. And then for the second one, what are we left with? Well, for the second one, now we're left with how do we deal with the integral of tangent. And so let's kind of keep going with this problem until we kind of get it to the very end. All right, so for this first integral, what we can do is we can employ our strategy and say we take out a secant. And so now that's going to give us a secant of x, tangent of x, dx. So that we can do our u substitution on that one. And now for our second integral, how do we deal with the integral of tangent? Well, now we remember what that is in terms of sines and cosines. That our tangent is going to be sine of x over cosine of x. And this will also let us do a u substitution. So for the first integral, what we want to do is a u substitution with u equal to secant of x, so that our du becomes secant of x, tangent of x, dx. For the second integral, we want to do a u substitution with u equal to cosine of x, dx. Whoops, cosine of x. Sorry, no dx yet. So that our du then just becomes minus sine of x dx. And so in that case, what happens is in the first integral, we end up with something that looks like u du. And in the second integral, we end up with something that looks like 1 over u du. And so those, again, become integrals that we are able to do. So we have a 1/2 u squared plus a natural log of the absolute value of u plus our arbitrary constant. And so kind of coming back to what our u substitutions were. So for the first one, our 1/2 u squared, u was secant of x. So this gives us a 1/2 secant squared of x. For the second one, for our natural log, that was cosine. So we have natural log of the absolute value of cosine of x plus our arbitrary constant. And so this lets us then evaluate our integral. That what did we start with? We started with just the integral of tangent cubed dx. And so we still can employ this strategy, even in that case, for what happens if we don't have a power of secant that we can borrow. We can still, if our power of tangent is odd, then we can still borrow from that and go forward as well. If tangent is only to the first power and we don't have any more secants, well, that was the case that we were dealing with here. If our power of tangent is greater than 1, so we've got 3, 5, 7, whatever, now we can take out a tangent, and that will still give us secants that we can, that will give us an even power of tangents that we can convert to secants, and to then give us something where we can employ our strategy again. So kind of the first case of things that we can deal with. So let's kind of maybe wrap that up or kind of summarize what we're about. And so the summary of this being that if we were dealing with secant to some power times tangent to some other power, if n is even, then we take out a power of secants. Then what do we do with that one? We take out a secant squared and convert remaining powers to do a u substitution with u equal to tangent. If m happened to be odd, then what could we do? Well, now we take out a tangent we convert powers to secant, and then what this sets us up for is to do a u sub with u equal to secant of x. And so those two kind of strategies are what we have in play for this set of problems. So now we've kind of gotten through maybe about half of what we could do with some of our trigonometric integrals of this kind. So stay tuned for the next video, and we'll see if we can take this one step further. See you all next time.